Hi guys, I welcome you to my YouTube channel. IBM is my name, and today I want to take you to part 9 of Solve the Past Paper questions. Remember, we are dealing with AS Physics. We are dealing with AS Physics multiple choice questions, Physics 9702. This is kinematics and dynamics, and we shall be dealing with we are going to be solving past paper questions, and this is strictly going to be part 9. So without wasting time, I would like to take you to the document. Do not forget to subscribe, share the videos, download the documents in the video description so that you can print and follow the videos with a hard copy of the documents. So without wasting time, I will take you to the document. So I think in part 8 we stopped on page 74, and in part 9 I want us to start from page 5. Which statement about a perfectly elastic collision between two bodies in an isolated system is correct? Of course, perfectly elastic collision kinetic energy must be conserved in addition to momentum. So A says both kinetic energy and total momentum are conserved. So the answer is automatically A without checking the rest. For all collisions, momentum is conserved, but for elastic collision, momentum and kinetic energy are conserved. Two spheres approach each other along the same straight line. Their speeds are u1 and u2 before they collide. After the collision, the spheres separate with speeds v1 and v2 in the diagrams shown. The collision is perfectly elastic. So if the collision is perfectly elastic, it means the total kinetic energy before collision is the same as total kinetic energy after collision, which means the relative speed of approach should be the same as the relative speed of separation. So the word relative means we subtract the speeds. For perfectly elastic collision, relative speed of approach should be equal to the relative speed of separation. So let's check the relative speed of approach. It's going to be u1 minus velocities to the right positive, velocities to the left negative, so it's minus negative u2. So that is u1 plus u2. Then relative speed of separation, these velocities, since v2 is since the second mass or the second sphere is ahead of the first sphere, it means v2 is greater than v1. So this will be v2 minus v1. This is the relative speed of separation. This is the relative speed of approach. So which equation must be correct? Automatically it is going to be D. Relative speed of approach equals the relative speed of separation. This cannot be correct because the word relative means we subtract the speeds. And since they're in the same direction, they are both positive, so the minus stays there. Here, they were in opposite directions. That's why this minus, when we combine it with this one, it became plus. So the answer is D. The diagram shows a man standing on a platform that is attached to a flexible pipe. Water is pumped through the pipe so that the man and the platform remain at a constant height. The resultant vertical force on the platform is 0. The combined mass of the man and the platform is 96 kilograms. The mass of the water that is discharged vertically downwards from the platform each second is 40 kilograms. What is the speed of the water leaving the platform? So let's first find the upward force. Let's first find the upward force which acts on the platform and the man to keep them in the same position. So the upward force F is going to be, of course, equal to the weight, which is simply m times g, which m is 96 times g, which is 9.81. So that is the force which keeps the man and the platform in the same position. Then according to Newton's second law, of course, according to Newton's third law, the force of the water downwards should be equal to the force upward. That's according to Newton's third law. Then from Newton's second law, the force is defined as the rate of change of momentum. From Newton's third law, the force is the same as the one I've calculated. Then from Newton's second law, the force is the rate of change of momentum. which is going to be equal to the mass times change in velocity divided by time. So the force is 96 times 9.81. 96 times 9.81. This should be equal to, they gave us the mass is 40 kilograms, so this is going to be 40. The mass of water that is discharged vertical downwards from the platform each second, the time is 1 second, so this is over 1 second. And the velocity is what is the speed of the water leaving the platform? So let's say it leaves with the speed v, and final velocity is 0, or it leaves with the speed u and the final velocity is 0, because the resultant vertical force on the platform is 0. That means the upward force is equal to the downward force. So if I know the downward force as the weight, by Newton's third law, the upward force is also equal to the weight. So if I try to find this speed u using my calculator, I'll simply say 96 times 9.81 divided by 40. So u is going to be equal to 23.5. So this is 23.5 meters per second. So the answer is going to be a C. The acceleration of free fall on the moon is 1.6 meters per second. The moon has no atmosphere. That means air resistance is negligible, so acceleration remains constant. An astronaut standing on the surface of the moon drops a feather. Remember, the moon has no atmosphere, so air resistance is negligible. Which graph shows the variation with time of the speed of the feather during the first second of its fall? The moon has no atmosphere, there is no air resistance, meaning acceleration remains constant. And remember, from a velocity or speed time graph, the gradient is the speed, is the acceleration. So the gradient equals to the acceleration. From a velocity or speed time graph, the gradient is the acceleration. Since there is no atmosphere, the acceleration will be constant and to be 1.6 meters per second squared. So the answer is going to be A. Because this is not a straight line, that will not, it means the acceleration here is not constant. This is actually, the gradient is decreasing, which means the acceleration is decreasing. Here the acceleration is increasing because the gradient is increasing. Here the acceleration is decreasing because the line is becoming horizontal, the gradient is decreasing. Here it is the speed which is constant. V is constant here because the line is horizontal, which means the acceleration here is 0. So the answer is going to be A. The gradient is the acceleration and it is constant since there is no atmosphere, no air resistance. A tennis ball is released from rest at the top of a building. Which graph best represents the variation with time of the acceleration A of the ball as it falls? Which graph represents the variation with time of the acceleration of the ball as it falls, assuming that the effect of air resistance is not negligible? So there is air resistance. So if there is air resistance, then as the speed increases, it means the resultant force decreases. So that means the acceleration decreases because the the force to air resistance increases. So the acceleration decreases and it goes to 0. The acceleration decreases to 0. And when the acceleration becomes 0, then we have reached terminal velocity. So the acceleration decreases to 0. So first of all, B is wrong because B is not tending to 0. B is now becoming, it means a point reaches where the acceleration remains constant. So it doesn't, this one is showing acceleration increases, acceleration is constant. The acceleration decreases to 0. So the only graph tending to 0 is A. I'm saying B is wrong because you notice that the line is becoming horizontal, yet if I prolong A, it could tend towards the x-axis, so it is going to 0. So the acceleration goes to 0. We reach constant velocity. we reach what we call terminal velocity. If there is air, we reach terminal velocity. So at terminal velocity, the acceleration will be 0. So the acceleration decreases to 0. The answer is A. A ball falls vertically onto ground and rebounds. Note that if it rebounds, opposite direction is very important. So if it rebounds, as shown, the ball has momentum P1 downwards just before hitting the ground. After rebounding, the ball leaves the ground with momentum P2 upwards. So it leaves the ground with momentum P2 upwards. The ball is in contact with the ground for 0.02 seconds. During this time interval, an average resultant force of 25 newtons acts on the ball. An average resultant force of 25 newtons acts on the ball. Okay, what is the possible combination of values for P1 and P2? So number one, I want you to notice that P1 is going to be greater than P2 in the first place, because in P1 the ball is falling, the speed increases. Yet in P2 the speed decreases because it's moving against gravity, so the momentum decreases. So P1 must be greater than P2 in the first place. Also, there could be a loss in kinetic energy on hitting the ground. So still it means there could be loss in kinetic energy on hitting the ground. So P1 is going to be greater than P2. That's number one. So P1 should be greater than P2. P1 should be greater than P2. So I ignore A and B. But then remember that force is the rate of change of momentum, and the force is 25 newtons. So 25 newtons is equal to the difference in momentum P1 minus negative P2. Because P1 is downwards, I can say it is positive. P2 is upwards, I can say it is negative. Divide by T. So this implies that when I get P1 plus P2 should be equal to 25 times the time, which time is 0.02. So it means P1, when I add P1 to P2, I should be able to get, I think this is 0.5. 25 times 0.2, 0.02, that is 0.5. So when I add P1 to P2, I should get 0.5. So let's check. The answer is automatically going to be C. When I add P1 to P2, I should get 0.5. So the answer is C. A sphere falls from rest through air. The graph shows it is falling from rest through air. Initial velocity should be 0, but it is through air, so the graph should reach terminal velocity, constant velocity. The graph shows the variation with the time of the sphere's velocity. Which diagram shows the forces acting on the sphere when it is at the velocity correspond to the point P on the graph? At point P, the acceleration is decreasing because the gradient, remember the gradient is equal to the acceleration. So at point P, the acceleration is decreasing, which means the resultant force should be becoming smaller. The resultant force should be becoming smaller. Okay, so which diagram shows the forces acting? So A is out because at point A, the acceleration is decreasing, yet this is showing that the forces are equal. Then B is also out because it is showing that there is a resultant force downwards, which would cause there is only one force downwards, which would cause an acceleration to increase downwards. C is going to be correct because as the air resistance starts increasing at point P, the acceleration decreases, so the gradient decreases, so the answer is C. D is wrong because D means that the resultant force F is upwards. It means F is upwards. The resultant force is upwards, so the gradient would be negative. Yet in the diagram we see a positive gradient. Gradient would be would be negative. The gradient would be negative. The resultant force is upwards, so this would mean slowing down. Yet what we are seeing, it is actually still speeding up, but at a smaller rate. So the answer is C. A ball of mass m traveling at a speed u collides with a stationary ball of mass m. After collision, the two balls travel at velocities v and v, small v and capital V respective, in directions shown. The student writes three equations relating to this the collision. Which row in the table indicates the correct and incorrect equations? So mu, total momentum before collision, is equal to mv plus m capital V plus mv. Remember this was capital, the one of capital M was stationary, so it means this is wrong. Initial momentum is fine, but this one is going to be wrong because the velocity is at an angle, so that is incorrect. Mu is equal to mv plus mv. This is incorrect. You can't say that this is correct. It is incorrect. Then let's check mv sine theta. We resolve this vertically upwards. Small mv sine theta goes upwards, and capital M, capital V sine 40 goes downwards. So I think this is correct. This is correct. So when you say this is incorrect, then you are the one who is not correct. So because this is correct. Okay, but we have three corrects here. Then let's check the last one. Mu equals to mv cos theta, cos 30 plus mv. So when I resolve these ones in the horizontal, we shall have mv cos 30 for the one above, and we shall have M capital V cos 40 for the velocity below. They are pointing in the same direction, so we add them. So this is also correct. So it means the answer is going to be, this is correct. This equation is correct. The first one is incorrect, so the answer is D. This is incorrect. This is correct. This is correct. So the answer is D. The ball rolls in a straight line up a ramp and then back down the ramp along its original path. Which graph shows the variation with the time of the ball's velocity? It rolls up, so the velocity decreases. Then down, there must be a change in direction. So B is wrong because the velocity is in one direction. It is both positive. For both parts of the graph, it is positive. So the velocity is in one direction. There has been no change in direction. D is also wrong. There is no change in direction. The velocity is still positive. So here, no change in direction. The same thing applies to this. There is no change in direction. So let's look at A and B. Now C is wrong because this one means that the ball bounced. This one means this is wrong because this one means bounced. Because you see it has bounced and the acceleration is the same because the lines are parallel. So this one means bounced. But then it means the answer is A. When it is going up, the velocity decreases to 0. When it reaches the maximum height, velocity here is 0. Then it changes direction. So this part here is showing a change in direction. Here V is 0 at maximum point, at maximum height. And here V is negative. There is a change in direction. So the answer is A. A ball is thrown with a velocity V at an angle theta to the horizontal. The acceleration of free fall is just assume that air resistance is negligible. Of course, it means acceleration is constant. Equations of motion can apply. What are the horizontal displacement x and the vertical displacement y after time t. So I'll use a simple equation. S is equal to ut plus a half at squared. S in the horizontal will be x equals to this part here. Acceleration in the horizontal is 0. Acceleration in the vertical is going to be g, but negative since it moved against gravity. So this is 0. So we have u. We resolve v in the horizontal. V to the horizontal will be v cos of theta, and the v to the vertical will be v sine of theta. So this is going to be v cos theta then times t. That is for the horizontal vt cos theta, so I ignore sine. Then for the vertical, it is y. So where there is s, I'm putting there y. Initial velocity in the vertical is going to be v sine of theta then times t. But since it moved against gravity, I have a minus a half g times t squared. So this equation is going to be vt sine theta minus a half gt squared. So the answer is going to be B. A ball travels from point X to point Y around a semicircular track of radius 1 meter as shown. What is the displacement of the ball from X to Y? So the displacement is the shortest distance between X and Y, which is going to be this distance here. And that distance, I think that distance is equal to the diameter of the circular path, because if this is semicircular, so that distance xy is equal to the diameter of the circular path, which is 1.0, which is the radius, plus 1.0. So this is 1.0 plus 1.0 to form the diameter of the circular path. So that gives us 2 meters. So that is 2 meters, but we have to, displacement is a vector quantity, we need the direction. So we ignore these ones. So 2 meters has no direction, but 2 meters due south. X, Y, that is due south. X to Y, that is due south. So it is 2 meters due south, because displacement is a vector quantity. This is a vector quantity. So the answer is B. Which row in the table gives the quantities that are conserved in a perfectly elastic collision? For perfectly elastic collision, both kinetic energy and momentum are conserved. Perfectly elastic, both kinetic energy and momentum are conserved. So momentum conserved, we ignore C and D. Kinetic energy is also conserved, so the answer is going to be A. Two equal masses travel towards each other on a frictionless track at speeds of 60 centimeters per second and 30 centimeters per second. They stick together. So that means it becomes a common mass. Now velocities to the right, I can say positive. Velocities to the left, negative. So let's find a conservation of momentum. Total momentum before. They have equal masses. Let this be m, m. Total momentum before will be m times 60 plus negative. So it becomes minus m times 3 times 30. I'm not converting the units because I know they are going to cancel out. So this should be called total momentum after. Since they stick together, their masses add up. So it becomes 2m. They move with the common velocity, which I'm going to call Vx. So m cancels. Vx is going to be equal to, that is 60 minus 30, which is 30, divided by 2, which is 15 centimeters per second. So Vx is going to be 15 centimeters per second. The Icarus satellite has a mass of 320 kilograms and moves through space using a solar sail of area 20 meters squared. The average solar wind pressure is 1.0 times 10 power 5 minus 5 newtons per meter. What is the acceleration of the satellite caused by the solar wind? Okay, so we want the acceleration of the satellite. So that means we need the resultant force. Resultant force is mass times acceleration. But remember, from pressure equals to force over area. the force is pressure times area. So MA is going to be equal to pressure times area. So the acceleration is going to be the pressure times the area divided by the mass. So the pressure is 1 times 10 power minus 5 times the area, which is going to be 20, divided by the mass, which is 320. That gives us 1 exponent minus 5 by 20 divided by 320. So this is 6.3 times 10 power minus 7. 6.3 times 10 power minus 7. So this means the answer is going to be B. A cyclist pedals along a raised horizontal track. At the end of the track, he travels horizontally into the air and onto a track that is vertically 2 meters lower. The cyclist travels a horizontal distance of 60 meters in the air. Air resistance is negligible, which means equations of motion can apply the Stewart equations because acceleration is going to be constant. What is the horizontal velocity v of the cyclist at the end of the higher track? Okay, that is quite easy. So I'm going to use S equals to ut plus a half at squared. This is the most common equation for projectiles. So if I consider horizontal motion, I'll call it HM, horizontal motion. S is going to be 6. Initial velocity is v, then the time taken is t. Remember, acceleration in the horizontal is 0, so this part will be 0 if I consider horizontal motion. If I consider vertical motion, using the same equation, S equals to ut plus a half at squared, the vertical distance is 2. Initial velocity in the vertical is 0 because we moved horizontally, so that is 0 plus a half. Acceleration is 9.81, then times t squared. So t is going to be equal to, I'll just calculate t. 2 times 2, which is 4. 4 divided by 9.81, square root of the answer. So t is 0.64. T is 0.64 seconds. So then I'll just go and substitute for t in that equation. So 6 is equal to v times 0.64 seconds. So I'll just say 6 divided by the answer, which gives me 9.4. So v is 9.4 meters per second. So the answer is going to be B. The astronaut on the moon, where there is no air resistance, throws a ball. The ball's initial velocity has a vertical component. So the vertical component is 8 meters per second, and the horizontal component is 4 meters per second. The acceleration of free fall on the moon is 1.62 meters per second squared. What will be the speed? What will be the speed of the ball 9 seconds after being thrown? Okay, 9 seconds after being thrown. So I want you to recall that the velocity in the horizontal remains constant. So velocity after 9 seconds it will still be 4 meters per second in the horizontal. Velocity in the vertical is the one which will change. Velocity in the vertical will be got from initial velocity in the vertical plus the acceleration in the vertical times t. I'm using v is equal to u plus at. So the velocity after 9 seconds will be initial in the vertical is 8. Of course, I don't resolve, it is already a component. Because it moved against gravity, remember acceleration in the vertical is going to be negative of the value of g. So this will be minus 1.62 on the moon. The time is 9 seconds. So I'll check with my calculator. So this is 8 minus 1.62 times 9, which is negative 6.62. 6.58 meters per second. So the resultant velocity is going to be the square root of 4 squared plus negative 6.58 squared. So I will just square that plus 4 squared. Then I find the square root of the answer. So I'm getting 7.7 as the resultant. The resultant is 7.7 meters per second. So it means the answer is going to be B. A car is traveling at a constant velocity. That means acceleration equals to 0. At time t equals to 0, the driver of the car sees an obstacle in the road and then brakes. So the final velocity goes to 0. The graph shows the variation of the t of the velocity. How far does the car travel in the 5 seconds after the driver sees the obstacle? How far does the car travel in the 5 seconds after the driver sees the obstacle? A car is traveling at a constant speed. At t equals to 0, the driver sees an obstacle in the road. That is, so the driver sees an obstacle at t equals to 0. Okay. So we need distance, which is going to be the area under the graph. So you can take this to be a trapezium if you want. The distance is going to be a half. Area of a trapezium is a plus b times height. Or you can take this as a rectangle, which will be 20 times 0.8. 20 times 0.8 plus this one will be 20 a half times 20 times this distance, which is going to be 4.2. But I'll just take it as a trapezium, a half into 0.8 plus 5, then times 20. If I take it as a trapezium, so this is going to be like the height. This will be A, B. B is the whole of this. Area of a trapezium is a half into A plus B times H. So we are taking this as a trapezium. So this gives me 0.5 times 5.8 times 20. So that is 58. So this is 58. So the answer is C. You can check with the other formula. 20 times 0.8, that is 16. Then a half, 0.5 times 20 times 4.2, that is 42. So 16 plus 42 still gives you 58. So you can divide the shape into the triangle, the shape into something you can easily deal with. So the answer is C. A car is stationary at traffic lights. When the traffic lights change to green, the driver presses down sharply on the accelerator. Sharply. The driver presses down sharply on the accelerator. The resultant horizontal force acting on the car varies with time as shown. Okay, so here acceleration here is 0. Acceleration here is constant. Which graph? Because remember, force is directly proportional to acceleration because force is equal to ma. When the force is 0, the acceleration is 0. When the force is constant, the acceleration is constant. Which graph shows the variation with the time of the speed of the car? So the answer here is automatically A, because for the first part, where the force is 0, the acceleration should be 0. And that means the gradient should be 0. So we have two options. We have this option here. Anyway, for all of them, they are starting from 0. There's no problem with that. But then for the second part, the force is constant, meaning the acceleration should be constant and it is not 0. The second part. Yes, here it is showing that the acceleration, the acceleration first decreases because the gradient decreases along that before it becomes constant. The same applies with this one. It is showing that the gradient first increases, then decreases before it becomes constant. This one is automatically showing that acceleration is increasing because the gradient is increasing. here it shows an increase and then a decrease in acceleration. Here it shows a decrease in acceleration before it becomes constant. So here the acceleration decreases to 0. Here it first increases, acceleration increases, then decreases to 0. Because the gradient first increases, then decreases to a constant gradient. So the answer is A, because here the acceleration is 0, because the gradient is 0. Then here the acceleration is constant because it's a straight line, which means the gradient is constant. A beach ball falls vertically from a high hotel window. Air resistance is not negligible. If air resistance is not negligible, it means acceleration due to gravity is not constant, it decreases. Which graph shows the variation with the time t of the acceleration a of the ball? Because air resistance is not negligible, the acceleration must decrease. B is wrong because it shows that the acceleration is constant. A is wrong because it shows that the acceleration increases. Here, the acceleration is increasing. Here, the acceleration is constant. Then D is automatically wrong because also it shows an increase in acceleration even though it becomes constant later on. So the answer is C. As the ball falls, the force due to air resistance increases, which means, remember, the resultant force is going to be the weight minus the force due to air resistance. When the force due to air resistance increases, the resultant force decreases. And the resultant force is given by mass times acceleration. Because the resultant force decreases, the acceleration must be decreasing. So the answer is C. A car has mass m. A person needs to push the car with a force F in order to give the car an acceleration of A. The person needs to push the car with a force twice F in order to give the car an acceleration of 3A. Which expression gives a constant resistive force opposing the motion of the car? If you remember, we had attempted a similar question. The answer is most probably going to be A. Let's check and verify. For the first force F, resultant force is given by mass times acceleration. This is going to be equal to the pushing force F minus the friction force small f. I'll use small f for friction. Then if the acceleration is 3A, so the resultant force is going to be m times 3A. Then this is going to be the applied force is twice F minus the friction force small f if friction remains constant. So the only way I will solve this, I'll multiply this equation by 2. And then I add the two equations, or I subtract. So this is equation number 1, equation number 2. So equation 2 minus equation 1, we have 3ma minus ma, which is going to be 2ma. This should be equal to 2f minus 2f, so 2 capital F cancels out. Then I remain with minus f minus f. Remember, I'm subtracting, so it is minus f minus negative 2f. I multiply the first equation by 2, remember? So this is 2f, 2 minus 2f. So that means twice no, when I multiply the first equation by 2, the first equation by 2, let me just multiply it here. The first equation by 2, it becomes twice ma equals to twice f minus 2 small f. Then the second equation is 3ma equals twice f minus f. So I'm subtracting second minus first. So when I subtract, I have ma equals to 2f has cancelled, minus f minus negative 2f. So it means f is equal to ma. Capital F cancels out, so the answer is going to be A. A box is shown resting on the ground. Newton's third law implies that 4 forces of equal magnitude are involved. These forces are labeled P, Q, R, and S. Forces P and Q act on the box. P and Q act on the box. Forces R and S act on the earth. Okay. For clarity, the forces are shown slightly separated, just for clarity. Okay. Which statement about the forces is correct? P is the equal and opposite force to Q, and both are forces of contact. Since P and Q act on the same object, then they are not both contact forces, because the contact forces, one acts on the other object, the other one acts on the other object, so this is out. Q is the equal and opposite force to P, and both are gravitational forces. P, they said P and Q act on the box. So P acts on the box, okay, and the Q acts on the box. Q is the equal and opposite force to P. Since they are both acting on the box, then Q is not the equal and opposite force to P. Then R is the equal and opposite force to S. Since both R and S are acting on the earth, then they are not the equal and opposite forces to each other. S is equal and opposite to Q. Remember, S is from the earth. The force P acts on the box, S acts on the earth. Those are equal and opposite, so the answer is D. Because from Newton's third law, the two forces must be acting on different objects. S is the equal and opposite force to Q, and both are gravitational forces, so the answer is D. Two spheres travel along the same line with the velocities u1 and u2. They collide, and after collision, their velocities are v1 and v2. Which collision is not elastic? Remember, for elastic collision, the relative speed of approach, u1 minus u2, because u1 is in the same direction as u2. If collision occurs, u1 is greater than u2. Then after collision, this is called relative speed of approach. Relative speed of separation is going to be equal to v2 minus v1. So v2 is going to be bigger than v1. So u1 minus u2 should be equal to v2 minus v1 for the collision to be elastic. So let's check. u1 minus u2, here it is going to be 7. 2 minus negative 5 is 7. Minus 5 minus 3. So it becomes minus 5 minus negative 2, that is minus 3. So this one is not elastic automatically. Let's check this one. 3 minus negative 3, which is 6. 0 minus 6, or 6 minus 0, which is 6. 3 minus negative 2, which is 5. 6 minus 1, which is 5. That is elastic. 5 minus 2, which is 3. 6 minus 3, which is 3. That is elastic. So the answer is A. A is not elastic. A lorry travels at a constant speed and then decelerates until it stops. Constant speed, then decelerates until it stops. So final velocity should be 0. Which graph shows the variation of time of the distance? Since it is a distance time graph, remember speed is the gradient. Speed equals to the gradient. Since it is a distance time graph, speed is the gradient. Okay. Remember the final velocity, the final speed is 0. So the gradient should be 0 at the end. The gradient should be 0 at the end, which makes C to be wrong automatically. It makes C to be wrong automatically. It travels at a constant speed, which means it should be initially a straight line. Constant speed, straight line for distance time graph. Straight for constant speed. This is a curve, so this is out. So this is a straight line. This is a straight line, this is a straight line. Then it decelerates. When you say decelerates, the acceleration is negative. That means the velocity decreases. The gradient should decrease. The gradient then decelerates until it stops. So the gradient should decrease until it stops. So when you look at the graph, since it is decelerating, it means the answer is going to be A, because here the gradient is decreasing until it becomes 0. So the answer here is going to be B. Initially a straight line, which means the velocity is constant, then a curve, which means the gradient is decreasing. So the acceleration is because the velocity is decreasing, it means the acceleration is negative. So then finally it becomes a horizontal line. That is when the velocity becomes 0, it has stopped. So the answer is B. A girl is jumping on a trampoline. Which graph shows the variation of the girl's velocity v with time t? Jumping on a trampoline. Which graph shows the girl's velocity? Which graph shows the variation of the girl's velocity v with time t? Okay, so since let us assume acceleration due to gravity is constant, g is constant. If there is no air resistance, g is constant. So how do we show that g is constant? First of all, remember for velocity time graph, acceleration is equal to the gradient. Acceleration is the gradient for a velocity time graph. So if the acceleration is constant, then it means this one is wrong and this one is wrong because their gradients are not constant, they are not straight lines. Number two, the acceleration is constant and the gradient should be constant to show that the acceleration is constant and should be the same for all. So that means this one, it should be same sign, same sign. That means the gradient should be constant with the same sign. So we have to look at this one here shows this is acceleration negative, a positive acceleration, negative acceleration. Yeah, so the answer is going to be D because this is vertical. This is a vertical line, which means the velocity just switches from one direction to another direction. There's a change in velocity with no time, so there's no acceleration there. But this line is parallel to this one, which is parallel to this one, which means the signs of the acceleration is the same. Because when you jump up and down, the acceleration continues to point downwards. So it means the answer is going to be negative because initially you jumped up and it remains negative throughout. The gradients here are negative, so the answer is going to be D. The gradient should be constant and should be having the same sign. Here the gradient is negative, here it is positive, negative, positive, Yet here the gradient is positive throughout. So the answer is D. In order that a train can stop safely, it will always pass a signal showing a yellow light before it reaches a signal showing a red light. Drivers apply the brakes at the yellow light, and this results in a uniform deceleration, negative acceleration to stop exactly at the red light. The distance between the red and yellow lights is x. Okay, distance between the red and yellow lights is x. If the speed of the train is increased by 20% without changing the deceleration of the train, what must be the minimum distance between the lights? Okay, so if the deceleration is constant, I'm just going to use v squared equals to u squared plus 2as. Before we change the speed, before we increase the speed to 20% initially, if it comes to rest, final velocity is 0 but squared, equaling to the initial velocity, which is u squared minus, because it is a deceleration, the acceleration should be negative, minus 2 times the acceleration times, I'll call that one the distance traveled, x, because the distance between the red and yellow lights is x. Okay, so that is times x. So this means that u squared is equal to 2ax. Then I'm now going to consider a situation where the speed of the train is increased by 20%. So initial final velocity is still going to be 0 because it comes to rest, but the speed has been increased by 20%. So that means the initial velocity is going to be 20 plus 100, that is 120%, 120%. So 120% is going to be 1.2 times u. So this will be 1.2 u, but this is going to be squared. It is 100 plus 20, which is 120%, or 1.2 times u. I just divided 120 over 100 of u. That is 120% of the initial velocity we considered in the first part. So this will again be minus 2 times a, then times the distance now between the lights will be, I'll call it s. I'll leave it as s. So what does this imply? This implies that this time, when I square 1.2, I think I get to 1.44. 1.2 squared. That's 1.44 times u squared should be equal to 2as. Okay. So I'm going to just combine these two equations. I'll combine these two equations. Maybe I can divide the two equations. I'll say 1.44 u squared divided by u squared equals to 2as divided by 2ax. So this one cancels, u squared cancels, so it means s should be equal to 1.44 times x, because 2a cancels out. So the answer is going to be C. Two frictionless trolleys are moving towards each other along the same horizontal straight line. Their masses and velocities are shown. The trolleys collide and stick together. Since they stick together, they move with a common velocity. What is the velocity of the trolleys after the collision? So let's find total momentum before collision. Velocities to the right positive, to the left negative. So for this one, its momentum is going to be 2 mass times velocity 1. For the other one, I will say minus because it is in the opposite direction, 3 times 4. This is the total momentum before collision. It should be equal to total momentum after collision. They stick together, so total mass will be 5, or 3 plus 2, which is 5. Then times the common velocity v. So I have 2 minus 12, which is minus 10, should be equal to 5v. So v is going to be minus 2 meters per second. The minus shows that this velocity is going to be to the left, because I said velocities to the right positive, velocities to the left negative. So it is 2 meters per second to the left. So it means the answer is going to be A. A bullet of mass 80 grams travels at a speed of 300 meters per second. The bullet hits a target and stops after a time of 100 microseconds. 100 microseconds. What is the average force exerted by the target on the bullet? So by definition, force equals the rate of change of momentum. So this is going to be the mass times the change in velocity divided by time. The mass is 80 grams, which is 8 times 10 power minus 3. Then the velocity changes from 300 to stop, and it stops, so it is 300 minus 0. Then the time is 100 microseconds, which is 100 times 10 power minus 6. So I'll press my calculator. 8 exponent minus 3 times 300 divide by 100 exponent minus 6. So that is 24,000. So that is 24,000. So the answer is going to be D. Okay. So I think let part 9 should stop there. Let part 9 stop on this point, and we shall start from here on in part 10. So part 10 starts from here. I'm trying to finish this by the end of this weekend so that I record past papers for students who are going to sit October, November. I'll be recording past papers year by year, both AS, A-levels, and then IGCSE. At least I'll be recording past papers. So I want to finish the series of kinematics and dynamics very soon. I think this video was helpful. In case you noticed something which was not clear, just write to me. Anything you don't understand, just inform me. I can try to give more explanation. Otherwise, I think I've tried my level best. Until next time, bye.